Can you see my screen?
Yes.
Yeah, can you see my screen?
Yes.
All right, so okay, just let me set things up a little bit. All right. Okay. So we proved chain rule. So which is so here the most important thing is the statement, not the proof. Okay. The most important thing here is the statement. I mean, you can the proof you can forget, no problem, but the statement you should never ever forget. Okay. So we'll use this one to show some things. Mainly, first answering the question that uh, how do you find the linear transformation lambda, which is derivative, right? So we have seen examples where partial derivatives play an important role, right? So we will first deal with that question. So today is 6th. All right. So question was, how do we find the derivative of a map f from Rn to Rm? So given that let's say of a differentiable map. Right. So differentiable map means that there is the existence of the linear transformation, which is the derivative. But we still don't know how to find that linear transformation. In examples from R2 to R, yeah, we have seen that partial derivatives play a nice role. So we actually proved this rigorously, that the partial derivative does play an important role, and it gives what actually we require. Okay, so the first question is, if f is differentiable, does the partial derivatives exist?
Yes.
Yeah, Akash, why? Why is that so?
Because partial derivatives are, after all, a directional derivatives in the direction of the coordinate axis, and if the derivative exists, then directional derivative should also exist.
Oh, no, 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 no. I mean, so we have not gone through directional derivative yet, right? Well, you should look at the limit.
So can we say that if the derivative exists at say x comma y, then lambda of x comma y is well defined, and lambda of x comma y is just the directional derivative of x I mean plus x times x plus that at y times y. So
Say that again. You're giving some interesting stuff. Okay.
so if say the map is differentiable at x naught y naught, say it's an r squared,
So
then
yes, let's take from r squared to
r
r.
yeah.
R. Okay.
So say it's differentiable at x naught y naught, comma y naught.
Okay. It is differentiable at. at x naught y naught. Okay.
So this means that there exists a map lambda which is well defined such that lambda of h comma k
Yeah.
is equal to the del f by del x at x naught comma y naught times h plus.
Well, yeah. So that part we want to show actually, right? So you see here, yeah. Let's look at
Sir,
this example. Yes.
we can also geometrically argue that if a derivative exists, that
Yes.
means that let's say a derivative exists at x naught comma y naught,
Ah.
then the tangent plane in that point exists. And if the
Right.
tangent plane exists, then if you look at the cross section, let's say del x comma y naught, that is we are fixing y naught and looking at the change of derivative in the cross section x. So if the tangent
Mhm.
plane at x naught y naught exists, then definitely tangents exist on the cross section. So partial derivatives have to exist.
Right. So geometrically, so that would be yeah, that would be one argument. Yes, right. So the question here is how does this lambda, and question is, if partial derivative exists, then can you give the partial derivatives in terms of lambda, right? So here f is differentiable means there exists lambda from R2 to R linear such that you have this limit h, let's say hk tends to 0, f of x naught plus h y naught plus k minus f of x naught y naught minus lambda of hk norm by norm of h comma k is 0. This much you know, right? Now, can you find partial derivatives out of here?
Yes,
So,
lambda of 1 comma 0 and lambda of 0 comma 1 will be the partial derivatives, right?
right, right. So that is the point. That is of course, and that is the same thing as if you look at tangent plane and look at the tangent of the curve intersecting the surface here, surface and the plane parallel to, let's say, x-axis. Sorry, xy plane parallel to zx plane and yz plane. Those both things are uh, corresponding to this intersection would give you a curve, and this tangent to that curve will be the partial derivatives. So here, yeah. So here it is very simple. So if you want to find, so the point is you want to get the definition of partial derivatives out of here, right? So what do you want to do? You want to put k to be 0, and you want this limit h tends to 0, norm of f of x naught plus h y naught minus f of x naught y naught minus lambda of h comma 0, right? And norm of h comma 0. Now this norm becomes mod, and this is in R. So this is nothing but limit h tends to 0, mod of f of x naught plus h comma y naught minus f of x naught y naught. And this is, since lambda is linear, so you get lambda of 1 0 times h mod by mod of h. And this equal to 0. This implies this equal to 0. So this implies lambda 1 0 h goes to lambda 1 0 h gives the partial derivative with respect to x, which means del f by del x is nothing but lambda 1 0. Yeah, everybody understand this? here, of course, you have at x naught, y naught. Yeah. Okay. Similarly, let me ask somebody. Yeah, Ananya, can you tell me what is del f by del y at x naught, y naught?
Hello, sir.
Yeah. Can you tell me what is del f by del y x naught, y naught?
The lambda into 0, comma 1.
Right. Lambda of, no, it's not into lambda evaluated on 0, comma 1. So this is a real number.
Yes, sir.
Yeah. All right. Okay. So this is how you get the partial derivatives. We want to generalize this one in more general context. All right. So this is what actually we wanted to do, but in a general state. So first thing is the following, a theorem. Let's call it theorem 1. Let f, which is f1, f2, fm from Rn to Rm be differentiable at a point A in Rn. Well, actually, we don't need it. We want to write this one as a if and only if statement is differentiable at a if and only if each fj, so 1 lesser equal to j lesser equal to m, is differentiable at a in Rn, and the derivative of f at a is nothing but df1 at a dfm at a. You see, dfa is a linear transformation from Rn to, yeah. So let me explain a little bit. So what is d of a? So dfa is a linear map from Rn to Rm, right? And fj, since f was a map from Rn to Rm, and fj was a map from Rn to R. So dfj is a map from Rn to R, linear, right? Now the claim is the claim of this theorem 1 is that this linear transformation from Rn to Rm is related by this. Each component you have one linear transformation. Now first question is, given a linear transformation from Rn to Rm, can you do this linear transformation in terms of this one? So this is exercise in linear algebra. So this is an exercise. So you should solve it right now. Suppose T is a linear transformation from Rn to Rm, linear. Then show that there exists Tj, j from 1 to m such that T of x is T1x, Tmx for all x in Rn. Yeah, this is very simple. But do you see this? Have you seen this exercise?
Sir, if we take the image of T, well, I mean, this is component wise linear, so we can take easily get easily T1, T2, and Tm.
Ah. Right. So this must have, I mean, m component, right? What you need to show m component is very clear because T is a map from Rn to Rm. The only point is that this should be all Tj. This component wise, it should be linear, right? This exercise is a trivial exercise, right? Yeah. So convince yourself this one. This is nothing to do actually. This exercise. This is kind of conceptual. You have here, since it is in Rm, you have m number of components here. Now you need to show each component is linear, and which comes from the fact that T is linear itself. Okay, so let us now look at the proof of the theorem on this side. Sorry, this side. So which means assume f is differentiable at a. Now we want to show each fj is differentiable. Yeah, anybody, can you have give an idea how to do this?
If f is differentiable,
So we can
then there exists a linear map. There exists a linear
Yeah,
map
yeah.
that there exists a linear map which represents the derivative of f. Now this linear map has like break this linear map into the tj's that we did above the in the lemma above, and each of these tj will correspond to the differentiation of fj. I mean
Yeah,
that's
but
the
how do you
idea.
know that?
Hmm?
Yeah, okay. Sadbhav, you were telling something?
I was just going to say similar thing. So fj minus tj,
Yeah.
this norm will be less than the norm of the total, the f
Okay.
minus lambda.
Yeah, right. Maybe let me give
This will be
you
less than epsilon.
right. Right. You can go through that one and try to do it by brute force. But I want to use the chain rule. Can anybody give an argument to using chain
You
rule?
can compose with projection maps.
Right. So projection maps are linear maps. So Sorin, can you tell me whether any linear map is differentiable or not? Yeah, Sorin,
Actually,
any linear map is differentiable or not?
it should be differentiable.
Yeah, why is that so?
I mean, because in terms when we do the differentiability, I mean, in the definition, we
Hmm.
just approximate it by a linear map.
Right. So,
So any linear map can be approximated by this map only, so it should be differentiable.
So what is the derivative? What will be the derivative of linear map?
I mean the lambda.
What will be the lambda? So given a linear map T, what will be the lambda?
Lambda is equal to t.
Yeah, can you prove that?
Yeah, from
From
the
definition.
definition, if we
Right.
take f of x plus h minus f of x minus lambda
Right.
by h, so we can just use the definition of linear map that t of x plus h is equal to t of x plus t of h, and
Hmm.
then we can show that lambda is equal to t.
Right. So any linear map is differentiable, hence projection is also differentiable. So we let's consider pi j is from Rm to R is projection. So jth projection, which is pi j x1 x2 xm, is nothing but 0 0. So we will not actually go to 0 because we are in R, so this would be xj. Right. So j 0 less or equal to j less or equal, so 1 is equal to j less or equal to m. Yes. So since every linear map is differentiable, pi j is differentiable, for each j, hence pi j compose f is also differentiable this is by chain rule, by the chain rule. So this implies so fj x is nothing but pi j compose fx. So this implies fj is differentiable. All right. So now the other way, assume that fj j from 1 to m are differentiable to show f is differentiable. Now here we'll use actually the exercise we gave here. So we'll formulate this one because we have tj's. So we consider lambda equal to df1 at a dfm at a, right? So that should be t1 t2 tm. So we consider this lambda. Now we want to show that this f is differentiable with the derivative lambda. So you want to look at f of a plus h minus f of a minus lambda h, right? We want to look at this one. So what will be this one? Can Sugata tell me?
Sir, f1 of a plus h
Mhm.
dot
F1 of
fm of a plus h minus
yeah. So now
dot
what will
f
be okay? So F1.
to
So
fm
you are
then
doing this one, right?
minus
A plus H minus F1A FMA, right? Minus,
yes sir
yeah. Then what will
minus
be this? Minus
d d of f1 and
D,
to d of f of fm h.
right? D of A, D of FMA, right? And H. Now,
Hmm.
so what is this? Right? You have all this minus. So this is what will be each term after doing this minus, doing this subtraction. Each component, what will be each component? So F1 of A plus H minus F1 of A minus D F1A H, right? So Fm A plus H minus Fm A plus H minus Fm A minus DFM A H, right? Is this fine? Now we need to look at the mod, right? Mod of or norm of f of a plus h minus f of a minus lambda h, right? So what will be it? Can you dominate by something?
We can use a triangle inequality to break
Yeah,
it into each some components.
right. So to use triangle inequality, then what will be the terms? Let's say j varies from
J varies from 1 to m,
1
and
to
each term would be fi a plus h minus fi
n.
a minus d fi a h.
Not I. We put j here, 1 to n, right? So fj a minus dfj a h, and what will be it? So what will be this modulus? So
We can just absolute value should be fine because it's just a single term.
right, absolute value is always fine here because this fj coming from Rn to R. Right. So now look at limit h tends to 0, norm of a plus f of a plus h minus fa minus lambda h by norm of h, which is less or equal to limit h tends to 0, summation j from 1 to m, uh, fj a plus h minus fj a minus dfj a h by norm of h. Here it's of course just modulus is enough. Okay, can you interchange the limit and summation? Maybe Tim, Janila, Jamir can tell. Can you interchange the summation and the limit?
Yes, in this case, since it's finite, the summation.
Okay, so finite sum gives you there, you can always interchange. Right. So you interchange it, and from m limit h tends to 0, fj a plus h minus fja minus dfj h by norm of h. So what is this limit? What is this limit?
F
Zero.
dash F.
Yeah, it's 0, right? So this is already there. If dash a is taken care of. And if dash a, of course, it will not be the case. Here fj. So this part is taken care of. So hence this limit is 0. And this is what actually we want to show, right? This is what we wanted to show. This limit has to be 0. So this implies limit h tends to 0 norm of f of a plus h minus f of a minus lambda h by norm h is 0. So it is differentiable. And we get, if we know the derivative of fj's, so we can actually get the derivative of f in this way. All right. Okay, so now we will use this one to find the derivative. Now it is clear for this. We want to try to find the derivative of this one. So finding derivative of each of the component is good enough. All right. Now next theorem says, so now here we would like actually, so you always trying to look at this as a linear transformation, but linear transformation has matrix representation, right? Yeah. So what will be the matrix representation of the derivative? Let's say with respect to the standard basis. Yeah, can anyone tell me?
It will contain the partial derivatives.
Right, it should contain the partial derivative, but what will be it? Can you guess?
Del fi del xj, something like this.
Right. So what will be the order of the matrix?
M cross n. There are m.
So it's going from Rn to Rm. Rn to Rm, right?
Yes, so m rows and n columns.
Right. Yeah, this is exactly the same. So we need to prove that. So theorem, what happened? Yeah, theorem 2. That so if f from Rn to Rm, so f is equal to f1 f2 fm is differentiable at a in Rn, then all the partial derivatives del fj by del xk exist for 1 less or equal to j less or equal to m 1 less or equal to k less or equal to n. The matrix representation of DFA with respect to the standard basis is del f j by del xk jk. Jk, of course, varies as before. That is, let us write the matrix del f1 by del x1 at a, del f1 by del x2 at a, del f1 by del xn at a, del f2 by del x1 at a, del f2 by del x2 at a, del f2 by del xn at a, del fm by del x1 at a, del fm by del x2 at a, del fm by del xn at a. All right, so do remember this matrix. So once you know this matrix, so once, see, we assume here f is differentiable. So if you know f is differentiable, then actually you can think of the derivative as this times h1 h2 hn, right? So that gives you, so a matrix corresponding to, so this t, let me just write it, a linear algebra fact. So suppose t from Rn to Rn is a linear transformation, right? Now t with respect to standard basis is nothing but a, let's say, a1 1 or 2, a1 n, a m1, a mn, right? Now Ankit, can you tell me, if your matrix is given, this one is given, how would you find t?
So can you repeat the question?
So suppose this matrix is given to you. So given a linear transformation, you can always get a matrix, right? With
So
respect
we
to
can
standard basis.
multiply this matrix with the element of Rn, like
Yeah,
x1, x2, dot xn.
right. So given the matrix, we get a linear transformation, something like h1 h2 hn goes to this a11 a1n m1 amn h1 h2 hn, right? So is this the same linear transformation of t as in t? Yeah, Arkodeep, can you tell me whether this linear transformation is same as the original linear transformation T?
Yes, sir.
Okay. Yeah, perhaps you have seen the proof, so I don't go into much details. So the point is that now once we know this, the matrix representation, you can always think of the derivative as in this form. So you can think of the derivative as the matrix. That was my point. You can always think of the derivative as this matrix. And this is very, very useful. Right? So you'll see why it is useful perhaps in the next class itself. Okay. So let us well, there is nothing actually to the proof. We already know the derivative. So the proof is here. Yeah. So this is the proof. Sorry. Yeah. Yeah. So this is actually the proof. Putting k equal to 0, and you have more variable, no problem. Right? So you get this one. So this is the proof here for the first part. So you want to show derivative of partial derivative exists. So you actually do this one. So to show the partial derivatives. So without loss of generality, you can look at m to be 1. So you have f from Rn to R. Now to show partial derivative exist, this means we already have this limit h tends to 0, or here should put that this h1 h2 hn tends to 0. This is in Rn, f of a plus h minus f of a minus here lambda, which is nothing but df at a h1 h2 hn. This norm by norm of h1 h2 hn. Right? Now we need to put h1 equal to 0, hj minus 1, and hj plus 1, so on, hn. So this implies limit hj tends to 0 mod of f of a1 hj minus 1 hj plus hj hj plus 1 an minus f of a1 a2 an minus df at a 0 0 0 0 hj 0 0 0 norm by norm of 0 0 0 0 hj 0 0, right? So this implies del f by del xj at a. So what will be it? Yeah. So what will be it?
Excuse me, sir, could you please repeat the question?
So what will be this equal to? Del f by del xj at a.
Uh, J times DFA of 0, 0 in everywhere except the jth place, which will have 1.
Oh, hj is not there right side, left side. So hj will not be there. Hj is actually the variable. So this is nothing but df at a
Oh,
0 0 0 0 0 1 1 at the which place?
at the jth place.
Right. This is at the jth place. So this will be it. So you see the partial derivatives exist, and partial derivatives is nothing but this one. Right? Now once we have this one, we know the matrix representation, right? Isn't it? You have t is a matrix. So what you have now is, let me go back to the linear algebra again. So you have t, a linear transformation from Rn to R, linear transformation, and you know, and we know the value of t 0 0 0 0 1 0 0 0 1 at jth place for all j. Let's look at this one to be just aj for all j equal to 1 to n. So what will be the matrix of t? Matrix representation with respect to the standard basis. Now you see, we are evaluating already in the standard basis, right? Isn't it? So what will be the matrix representation of t?
AJJ, when this means it should be a diagonal matrix.
Should be a diagonal matrix of order.
Sorry,
And Nitish, can you tell me?
it should be a row matrix.
A row matrix. Okay. So what is the row matrix? Or what is the entries?
A1, A2, A n.
Right. So t with respect to the standard basis is a, the order will be the order of the matrix 1 by n, right? Yeah, is it correct? Yeah. So you have one row and n column. Now what you use the previous theorem. So next you use the previous theorem, which we proved here for matrices for functions from Rn to Rm, and then each of matrix representation you have. Of course, you have here in terms of the matrix. How you need to see how the matrix representation will come of this form, right? So the following exercise is again a linear algebra exercise. suppose Tj from Rn to R is a linear transformation right. So for all j from 1 to m, now t is t1 t2 tn tm from Rn to Rm. So what is the relation between the matrix representation of T with respect to the standard basis of Rn and the matrix representations of Tj 1 less or equal to j less or equal to m with respect to the standard basis of Rn. Right, so once you know this answer to this question, you actually know the matrix representation of this DFA, and it should come like this. Okay, so the remaining of the proof is an exercise. So you have all the ingredients. Now you put things together and exercise. Complete the proof. You have all the ingredients. What you need to do is just to complete the proof. All right. So I'll stop here. So any question?
So,
Yes.
is it like all the TJs are columns of T?
All the TJs are.
Columns of T.
So see, I mean, you need to. So this has to be row, right? Yeah, this has to be column here. This has to be column here as a linear transformation. How does the matrix representation relate it? The matrix representation, right? So matrix representation, this will be 1 by n matrix. This will also be a 1 by n matrix. So how this? So and this will be an m by n matrix. So how this matrix representation of this and all this are related? So this is a little bit different question. Okay, so of course this as a linear transformation, it is related by this one. Do you understand? Is it clear now?
Yes.
Okay, so do that exercise and you'll solve it. You can get it.